All right. So, welcome everyone to our fluid mechanics discussion, week 16, get previous year questions. So, today I forgot to update this. Yeah. So, today we will discuss first question based on our open channel flow theory question. And second will be on kinematics. Or maybe we can say flow measurement. This eraser is a little smaller. Let me increase the size. Yeah. Still smaller. And second discussion will be on flow measurement. Both are theory questions for today. And then we will look into hydrostatic forces on plane surface. Two questions, one simple question, one little bit tricky if you want to call that tricky. And then we'll go ahead with that. All right, so let's start with the first question. GATE 2011, question number 18. The flow in a horizontal, frictionless, rectangular open channel is supercritical. A smooth hump is built on the channel floor. As the height of the hump is increased, choked condition is attained. With further increase in height of the hump, the water surface will, option A, rise at a section of upstream of the hump. Option B, drop at the section upstream of the hump. Option C, drop at the hump. Option D, rise at the hump. So first, let's see what is this question telling us. So we have a horizontal flow. Okay. So we have a horizontal bed, no slope. Very good. Frictionless. So there is no loss of energy. Total energy line is going to be horizontal. Right? Total energy line is going to be horizontal. Now this is supercritical. What does that mean? So if you know, in open channel flow, we have seen that the specific energy and the depth of flow that follows a curve like this. So this is a 45-degree line and this is the curve. That means for each energy level on the x-axis, there are two depth of flows. One above the line dividing these two, the higher depth is the subcritical and the lower depth is the supercritical. So we all know what is subcritical and supercritical. When the Froude's number is less than 1, we call it as subcritical. When the Froude's number is greater than 1, we call it as supercritical. We are all familiar with that. If you are not familiar with this, I will suggest you to look into it. Okay, so when the flow was as it is undisturbed going along on this horizontal bed, then let's say the energy was even, shown by this particular blue line that we have. And since it is supercritical flow, so this was the depth shown by the blue dot, right? But when we added a hump on somewhere along the downstream of the section, what did we do? We reduced the energy at the downstream side of this particular flow by the height of the hump. So this line, which is the specific energy line which we drew here, will shift to the left side, and let me use some other color, by the amount of delta Z. So this is the new specific energy for this downstream point, E2. Now what do you see from this particular figure? We see that in supercritical flow, if this thing happens, if you are adding a hump this and specific energy is decreasing, the depth of flow is going to increase. So if it was y1 before the flow on the upstream, it is still y1. After the addition of this hump, the depth of flow in the downstream is going to be y2, right? It has increased. Now what more they have told us? They have told that the height of the hump is increased, choke condition is attained. What is the choke condition? Choke condition represents the point where you are at critical stage. So from supercritical, you kept on increasing the height of the hump. So first it was delta Z1, then maybe you increased it to delta Z2, and you increased it till the point when choke condition was obtained. So your flow is now like this. So you have some delta Z. So this is your delta Z final. Now what happens? So in subcritical, what will happen? Let's see. In subcritical, when you had increased the hump size, the depth of flow decreased, right? The depth of flow kept on decreasing till you reached this supercritical. So till you reached the critical point. And after that, what happened? After that, the depth of flow was maintained at this particular downstream end, and when you still kept on increasing the hump size, this depth of flow was constant, but the upstream side depth started increasing. But in case of supercritical flow, if you think intuitively, ignoring the concept of hydraulic jump, because in actuality, if you think what is going to happen in this case is when you still increase this particular hump size, there is going to be a hydraulic jump that is going to occur, where the depth of flow on the upstream will be very low, and then there will be abrupt increase in the flow depth. That is the hydraulic jump phenomena that is going to occur. But just think from this curve perspective. Just think from this curve perspective. What is going to happen? See, the energy on the downstream side, ignore the concept of hydraulic jump for now. Just think about just from this curve perspective. In the subcritical flow, when you had increased your delta Z to the limit, the downstream energy became the critical energy, and it cannot go below this, right? But what are you doing? You are trying to decrease this particular energy at the downstream side yet again by delta Z amount. So to keep this energy constant on the downstream side, the energy on the upstream starts to increase by increasing the depth height, right? By increasing the upstream depth of flow, in case of subcritical, this particular E1 starts to increase, so that E1 minus delta Z still remains constant. So by using this logic, if you think, in case of supercritical flow, again critical energy is attained at the downstream side by giving the maximum delta Z possible, and E1 is the energy, and this relation is still valid. So if you yet again decide to increase your delta Z, this EC, the critical energy at the downstream, has to remain EC. So what will happen? Your upstream energy even has to increase, as same as in the case of your subcritical flow. The upstream energy in the supercritical flow also at the upstream, it has to increase. So what will happen from this curve? What can we see? So up the energy, when it increases in case of supercritical flow, the depth is going to decrease. You can see this curve is going down. This curve is going down in case of supercritical flow. So the depth of flow is decreasing. So if you forget the concept of hydraulic jump, because in this question it is very clear that they are not asking uh, about hydraulic jump. So what will happen? If you keep on increasing the hump height beyond this critical point, beyond this particular critical point, the energy in the downstream has to remain constant because it has reached to the critical point. That means the energy and in the upstream side will have to increase. So that means the energy on the upstream side will have to increase to compensate that. And in case of supercritical flow, when the energy of flow increases, the particular depth of flow decreases. So that is what we are going to see. Let's check the options. Rise at the section upstream of the hump. That is not true. Drop at the hump. That is not true because we know it is going to maintain a constant level. Rise at the hump. That is not true. Drop at the section upstream of the hump. That is true because y1 decreases, E1 increases. That means E1 minus delta Z remains constant. That is easy. So B is the correct option. All right. Let's go to the next question. GATE 2010, question number 19. Group 1, Group 2. Group 1 gives us the list of devices. Group 2 gives us the list of uses. And we have to match them. All right. So what devices we have? We have pitot tube, we have manometer, we have venturimeter, we have anemometer. So this I don't think there is any kind of concept in this. This is the kind of question which you have to remember, right? Which you will remember if you practice. How I solve this question, I'll show you. So basically, what we have is anemometer. We all know is used to measure the velocity or the velocity of wind, right? We use, you would have seen in a lot of movies, you would have seen there will be drawing. You will see some like a hen will be on the top of a tower with some cups, right? With some cups on the perpendicular four axis. So these will be cups. So the wind will strike and they will rotate, and some kind of calibrated device will be uh, attached to it, and that will give us the speed of the wind. Or nowadays, more sophisticated equipments have come. So there is digital equipments with some fan inbuilt in them that will give the speed of the wind. So this particular anemometer is for the velocity of wind. We can also see that can also be called as velocity of air and gas. So S is 3. We know this. From movies, we know this, right? And manometer, we have done so many questions in our BTech related to manometer, right? There is a flow and sorry, there is a flow in this particular pipe. There is a another pipe attached to it with some mercury, and then from the difference in the level we determine the pressure, right? So Q is nothing but measuring the pressure in the pipe, right? So Q is 1. So if you just know these two, based on this itself you can solve this question. So let's see which of the options have Q as 1 and S as 3. Q not 1, Q is 1 but S is not 3, Q is 1 but S is not 3, Q1 S3. C is the correct answer. We don't even need to know about all the rest of the things, but for completeness we'll just see what are these things. So we know that S is 3 and Q is 1. Pitot tube. Pitot tube is, before pitot tube, venturimeter. Venturimeter is nothing but is a device used to measure the discharge in a pipe. So R is 4 and P is the pitot tube. It's nothing but a device to measure the velocity of flow in pipe. So it is 2. So P2 Q1 R4 S3. C is the right answer. All right. I hope you also understand that we don't need to know everything to solve questions in GATE. Competitive exams don't work like that. You have to use some kind of trick. All right. So that's all for the quota questions. Now let's look at some other questions. So we have, I have decided to discuss today some one simple question and one little tricky question, because these type of questions are not asked that much, and they are fairly simple when if they are asked also. So what we are going to do is we are going to look at two questions for hydrostatic force. So you would have seen these type of questions in your BTech, where we have submerged a plate inside a fluid, right? And then we are asked to uh, calculate the force on this particular plate, and where this where this force is acting. So the point of action and then the total amount of force. So we are going to look at this type of question. So let's see one simple question first. Square plate, side 1 meter, is held. So my apologies, this is not held vertically in water. If the top edge of the plate touches the water surface, the total pressure and its point of action on the plate is. So we have some kind of liquid, and then we have a square plate which is held vertically, and the top edge touches the surface of the water. So this is the side view, and let me erase this, and this is the plate looking like from the front, right? This is where the force will act, and this is the front side, and it is a square plate of side 1 meter, so this is going to be the dimension. All right, this is water, so rho we are going to take as 1000 kg per meter cube. G nothing is given, so 9.81 meters square per second. Sorry, meter per second square. Yeah. And now let's calculate the force. Couple of points. Point number one, total force is calculated using the pressure at the CG of the plane surface. So if this is a particular plane surface, and on that this force is acting, then what you have to do, you have to look at this plane area. What is the configuration of the area, whether it is a circle, whether it is a semicircle, whether it is a triangle, and then you have to identify the CG of this particular surface from the top of the fluid. So if this in this case we have a simple question, so this is just at the particular top of this plane is touching the surface of the fluid. So this particular height is going to be CG itself. But if, let's say, the plate was below, some height below this water surface, then you have to calculate the distance of the CG, and then you have to add this particular height also. And then the pressure at this particular height is going to be used. Rho g h1 plus hg is going to be used to get the total force. So this is the pressure you will get, right? And the force will be rho gh into this particular area of whatever you have, whatever kind of plane surface you have. If you have a curved surface, then you take the projected area. Okay. projected vertical area. All right. So this is first point. Second point, the point of action of hydrostatic force is not the center of gravity of the particular object. In fact, the if we say the depth of point of action is always greater than or equal to depth of CG of the plane surface. So if we say HP is the depth of point of action, it will be always greater than or maybe equal to also to the depth of center of gravity. And what is the formula to calculate this? HP is given as Hg plus Ig sine square theta divided by A Hg. What is Hg? We know it is the depth of the center of gravity. What is A? A is the plane surface area, or in curved case it is the projected area. Sine square theta is the where the theta is the angle of the angle the given plane makes with the surface of the water. So let's say this is your square plate. So this angle 90° is your theta. And let's say if this is your particular plate, then this angle is your theta. Okay, nothing too complicated. What is Ig? Ig is the moment of inertia of the plane surface area about the CG. Okay, that is your Ig. So moment of inertia about the CG for this given configuration. That is nothing but your Ig. So now let's solve this question. Let me just copy this. Okay. Now, what is the Hg? Hg is nothing but, since we have a square plate and the top is touching the surface of the water, it is nothing but A by 2, where A is the side. So it is 1 by 2, 0.5 meters. Okay. Now, based on this, can we calculate the total pressure force? Yes, we can. So total pressure force is going to be rho g h g a. So 1000 into 9.81 into 0.5 into 1 meter square area. So let's calculate this. 9.81 into 500, 4.9 kilonewton. Right? This is going to be your force. All right. Second question is, what is HP? It is the point of action of this horizontal force. So let's calculate that. For that, we need Ig. So here is a trick that I want to share with you guys. See, I don't usually remember all these formulas, for the center of gravity and all that. I try to remember the least that I have to remember. So that's why I'm going to share one thing with you that I don't know, maybe you already know this and or maybe you don't know this, but what you can remember is in case of our rectangle from the centroid it is BD cube by 12. So this is B, this is D. In case of triangle it is BH cube by 36 from the centroid. But what you can do is you can remember the moment of inertia about the base. It is BH cube by 12, right? And then how do you calculate based on the for the center of gravity? You just do this Ig plus 1 by 2 BH into h by 3 square is equal to BH cube by 12. So when you solve this, you will get BH cube by 12 minus BH cube by 18. And upon solving, you will see that it is, so let me do 36 here. And make this 36, we need 3 and we need 2. So BH cube by 36. See, some people say that you can memorize all the formula, you should memorize all the formula. But I personally don't like that. And if you share the same opinion, you can also use these tricks. So what I did here, I simply use the parallel rule for calculating the parallel theorem for calculating the moment of inertia. So you know that if you have a particular body or plane surface and you know the moment of inertia about the center of gravity CG, then you can calculate the moment of inertia about any other point which is at a distance x by CG plus area into x square, right? That is moment of inertia about the point. So what I used is, we know the moment of inertia about this point and we know the distance from the center and the area. We can calculate the moment of inertia about the center by subtracting it, right? So that's what I used here. Now just a little bit of sideline thing, that if you want, if you find this useful and if you also face some kind of difficulty in learning or remembering the formulas, then it is better to remember something like this rather than to use a wrong formula in the exam and get negatively rewarded or for your hard work in the exam. That is much more detrimental than spending, let's say, 1 extra minute or 30 extra seconds to get the formula. Okay, yeah, so those things aside, what is the Ig for rectangle? BDQ by 12. Here B is 1, D is 1, 12, 1 by 12. Theta 90 degree. So HP is 0.5 plus 1 by 12 into 1 divided by area is 1 and HP is 0, Hg is 0.5 again. So this is Ig, this is sine square theta, this is A, this is Hg. So we have 0.5 plus 2 by 12, right? 1 by 6. 1 by 2 plus 1 by 6. So we have here 4 by 6. 2 by 3 is the answer. HP is 2 by 3 meters, 0.67 meters from the top. All right, so this is how we do this kind of questions. This is a pretty simple question. I know most of you who are watching this will be thinking why we are doing this. This is just to refresh for most of the people. They would have even forgotten the formula of how to calculate this HP. So I am giving you guys the opportunity to refresh this before we go to the next question, so that we don't have any kind of excuse that we didn't remember this formula. Otherwise, we would have solved the next question also. Okay. So now let's go to the next question. This is a good question. An inclined gate AB. So this is an inclined gate. A and B are the extremes, it is shown, and it is rectangular, located inside the water storage reservoir. Some reservoir which is storing water, it is located inside that. And the gate is such that there is a hinge at this point A. So there is a hinge at this particular point A. Means this gate opens about this point A, something like this. Now, what is the force needed to be applied at point B to open this gate? So, what is the force that we will need to apply at this point B to open this gate? So, basically, this question is a kind of momentum balance question. So, you have to first calculate the force that the water is applying on this gate, and then you have to use that to kind of balance the force that you have to apply at the point B, and that F will be the answer. And AB we already know, it is given to it. So the cross section of this gate is 5 meter along, so into the page, and 1.2 meter here. So your AB is 1.2 meter. So you know the lever arm of your force, and you have to calculate the force. So for calculating that, first you need the actual hydrostatic pressure force that is being applied on this gate by the water, and you need the point or the height from this particular point A. What is the point of application of this force? So the HP that we get usually is from the top of the surface, but we need something else. We need HP star, that is from the hinge. All right, so let's start. First, let us calculate the pressure or the force, pressure force at this particular gate. For that, we need to calculate the center of gravity, Hg. So let me zoom in here. This is 1.2, correct? And if you look at this, the center of gravity is going to be somewhere here, 0.6, right? So this is 0.6. Okay. And what else we have? See, we have this. So this question may not be 100% accurate based on the geometry when you look at it. See, because this is 45 degree. What does that mean? That means that this particular thing, that is 5 meter is given to us, the height or the depth of the point B from the water surface, and this should be equal. Okay. Oh no, it looks fine only. So yeah, so ignore that earlier comment. Now this is 0.6. We need this height, h bar. How can we calculate it? We can calculate it using, if we know the depth of this point A from the surface, and this is also 45 degree. So let me give them some names so that it is easier to call them. So let's say this is given to us as A. Let's call this as CG, right? So let's call this as G. Let's call this as C. Let's call this as D. So H bar or HG, center of gravity, heights of center of gravity is DG, and it is nothing but DC plus CG. Can we get CG? CG is nothing but 0.6 divided by root 2, right? Because this is 45-degree angle, so CG is going to be 0.6 divided by, or 0.6 into our sine 45 degree. Sine 45 degree is nothing but 1 by root 2, so we have 0.6 divided by root 2 as our CG. It will be some value, let me write it here, 0.848. Now what is DC? How can we calculate DC? Very simply, you see here, can we calculate the vertical component or vertical projection of AB? Yes, 1.2 divided by root 2. So if you just subtract 5 from 5 this thing, then you are going to get the depth of A from the water surface. So your DC is nothing but 5 minus 1.2 divided by root 2. That is 4.151 meters. So your H bar is nothing but 4.151 plus 0.848. Alright, so I did a mistake here. See, you guys also didn't tell me. 0.6 divided by root 2. I wrote it as 0.848, right? It is 0.424. That's what happens when we don't just completely rely on calculator. So if we are dividing something by some number which is greater than 1, it is going to reduce, right? And it is going to be 0.424. Yeah. And then our DC was correct. So DC is nothing but 5 minus 1.2 divided by root 2, as we discussed. This is 1.2. Then horizontal vertical component of that is going to be 1.2 divided by root 2, and we subtract it from 5 to get the depth of A. That will be your DC, right? It is going to be 5 minus 1.2 divided by root 2, 4.151. So CG we know, DC we know, H bar now we can calculate 4 to 4, 4.575 meter. Now that we have done this, there was a much more simpler way to calculate this. That is probably what I should have shown you guys here. See, forget all this. What did we do here just now? We wasted some time, but one valuable lesson we learned. What did we do? We calculated this height and then we added it to this height. This was unknown to us, and this we calculated. This particular vertical component of this 0.6 meters is going to be same as this vertical component, because here also it is 0.6, because CG according to this particular rectangle face area is going to be in the center. So 1.2 is going to be divided into equal parts, 0.6 above, 0.6 below. So if we were to just subtract this vertical component of this 0.6 from 5, we would have much more easily gotten our answer, which will be same as what we had earlier. So here is something you can learn from my mistake. See, because of some extra calculations, some other mistakes happened, so which you can avoid by trying to do the problem with the steps where minimum calculation is required. So H bar is 4.575. Now let's calculate the pressure force from this particular H bar. What did we discuss about the pressure force? It is nothing but rho g h bar into area, right? Rho 1000, g 9.81, h bar 4.575 into area. What is it? 5 into 1.2. So what is the total force? We get 9.81 into 4.575 into 6. We have 269.28 kilonewton, right? This is our force that will act on this particular gate at some height that we have to calculate now. So we have calculated the force. We have to this question is asking about this force. We already know the lever arm for that force. Now we have to just calculate the location of the point of action of the force with respect to the hinge. Before that, what we are going to calculate is the actual point of action of this force from the top of the water surface, that is HP. So what do we know? We know that HP is nothing but Hg plus Ig into sine square theta divided by A Hg. So in this particular question, I actually wrote Hg as nothing but H bar. So we can here write it as, to avoid any confusion, sine square theta divided by A H bar. What is A? A we already know, 1.2 into 5, that is 6 meters square. Theta is given to us as 45 degrees. So sine square theta is nothing but 1 by 2. Ig is what? Ig is the moment of inertia of this plane about the CG. That is nothing but BdQ by 12. So let us calculate that. Base is 5. 1.2 is this length that is given to us. 1.2 cube divided by 12. So can we have the value here? Can you guys tell me the value? So you can do that calculation. Meanwhile, I will write this value here. 5 into 1.2 divided by 12. 0.72. Can you confirm whether it is correct? Meter to power 4. And H bar we have already calculated 4.757. So your HP is 4.575 plus 0.72 into 0.5, that is 1 by 2 from sine square theta, divided by 6 divided by 4.575. Can we know this value? .588 meters. Let me know if you are getting any other value. Right? So I think this is, I am getting correct value. So we are going to proceed with this. If you are getting any other value, please, you can recheck your calculation. Now, what we have gotten is this. So let me draw it again here. This is our hinge. This is our gate where we have to apply this force. This is B, this is A, this is 1.2, right? This particular angle is 45 degree. And we have obtained the height of the point of action of the force from water, which is 4.588 meters. But we have obtained this height from the surface of the water. What do we want? We want this value from the hinge. We want this. Can we calculate that? Yes, no, we can calculate it very easily, right? Because what else we know? We know that the depth of this, the depth of this point B is 5 meters, correct? And we know this is 5.88. So can we get this height? And when we know this height, using this 45-degree angle, can we know this length? Let me call it as y. So what we have to do, x will be nothing but 1.2 minus y. So let's calculate that. So the so the y will be 5 minus 4.588 into root under 2. Let me know if you understand this. What we have done simply, we have calculated this. This is nothing but 5 minus 4.588. So let me do it. It is 0.411 or 0.412. This is it. And this is 45-degree. And we want to know the hypotenuse. When this is 45-degree, that means the hypotenuse is going to be 0.412 root under 2. Right? Because this is 90-degree. So our y value is nothing but 0.412 into root 2, that is 0.582 meters. So the x value is 1.2 minus 0.582, that is 0.617 meters. Now we know everything that we need to know to calculate our force that is required to lift up the gate about the point A by applying a force at point B. Let me just put the values into this equation that we wrote originally. So FW 269.28 into the lever arm for this force that we just calculated, 0.617, is equal to the force required, that the force we need to apply to lift the gate, into the lever arm of that force. So we are going to apply this force at the end of this gate at the point B. So this is 1.2 AB. So the value of the force is 269.28 into 0.617 divided by 1.2. It is 138.45 kilonewton. Okay, these type of questions can be asked in this in the gate, and they have been asked in the gate. So I think this should be a good kind of revision for you guys. So what we have discussed, that's all. So this is the last question that we discussed today. So what we have discussed today, we have seen two questions from our quota related to theory. One is based on open channel flow. One is based on just the instruments and what are they used to measure. Second, we just saw a simpler question, simpler version of the question related to horizontal forces on a vertical plane. Then we saw a little bit complicated question, which was force on the inclined surface and the application of that, right? So that's all for today. Thank you, and I'll try to upload this video as quickly as possible. I know last time I said it, but I wasn't able to, but this time let's see if I can upload it. I'll upload it today itself. All right. Thank you. Okay, I'll end the session now.